Hello everyone, I'm Adyasha Mohanty, and today I'm excited to present our work done at Stanford under Professor Grace Gao called Tidally Coupled Graph Neural Network and Kalman Filter for Smartphone Positioning. Recently, hybrid methods which combine both learning as well as classical positioning methods have been shown to be really powerful for improving GNSS-based positioning in challenging areas. The reason being that learning-based methods by themselves are not able to fully utilize the known structure of satellite signal. However, existing model-based approaches such as weighted least squares or Kalman filters can really help us capture satellite geometry through known metrics such as dilution of precision or line of sight vector, as well as help compute expected measurements by using pseudo-interest residual and indicate signal quality by using carrier to noise ratio or pseudo uncertainty. In our previous work, we exploited a hybrid approach by combining a graph neural network or a GNN with a Kalman filter. This is the picture showing the framework. Initially, we had a Kalman filter which helped provide coarse positioning or coarse initialization and helped condition the inputs that were then sent to a graph neural network. The GNN then learned the positioning correction, which was used to compute the final position of the receiver. In the GNN, the structure used satellite position as nodes and conditioned measurements as features. These were conditioned by using known geometrical and measurement properties of the signal. Even though this work showed really promising results, there were certain limitations. First, the GNN was not able to adapt to dynamic graphs. The Kalman filter was manually tuned, and lastly, the GNN and the filter were optimized separately in a sequential manner. The contributions of this work are trying to improve on the limitations of our prior work. First, we improved the graph neural network by using an extended feature set and proposed a novel strategy for creating edges. And finally, we use inductive learning on the graph to learn representations which were previously not seen or present in the graph. Instead of using a manually tuned Kalman filter, we design a learnable filter by using backpropagation, a technique that is commonly used to train neural networks. And lastly, instead of sequentially optimizing the GNN and the filter, we deeply couple both components in our framework by jointly training them under a single optimization function. Here is the proposed framework for this work. Initially, we start with the raw measurements, which involve GNSS core phase, carrier phase Doppler, known satellite positions, velocities, as well as the coarse receiver position, which is inferred from a weighted least squares. We then perform feature processing to convert these raw measurements into a format that can be easily integrated into the learned Kalman filter. We then apply the predict step of the filter where we propagate the state by using known system dynamics and the covariance. And then in the measurement update, we then use the GNN observations to perform the next iteration of the filter. And then finally, given the estimate of the current position and our known position from ground truth, we compute the mean square error loss, which is then used to train this entire filter in an iterative manner. So in the backpropagation step, the filter parameters get updated, the GNN nodes are also updated in an adaptive manner, which then helps improve future versions or future estimates of the state. We also validate our approach on real-world datasets. Specifically, we use the Google Decimeter Challenge 2021 datasets, which are collected in different cities in California. We use about 49 training traces, showing example cities such as Mountain View and San Francisco, and then we test our approach on 13 testing traces collected in cities such as San Jose and Sunnyvale. Note that we also stress test our approach on using additional datasets in Los Angeles. If you are more interested in knowing about the results for this work, we suggest you to check out our work, which will be published in an upcoming issue of Navigation. Thank you so much.